Hello and welcome to Eng Phys 2P04 Lecture 17, Elasticity 1, Normal Stress and Strain. This is going to launch the start of our discussion of elasticity theory, where we're going to be looking at how materials deform in response to internal forces and moments. First off is axial stress and strain. Axial stress and strain result from an axial force. So a spring exerts a restoring force in response to a change in its length given by the spring constant, according to Hooke's law. In Hooke's law, the negative sign meant that the force opposes the change in length. So if you have an increase in length, a positive delta L, then the force of the spring is going to be in the opposite direction. It's going to act to try to restore that. This is the force of the spring, though, and in this section we're going to normally be talking about force on the spring. So what has to be the force on the spring to make it have that length change? Well, if it's extended, then there must be a force on the spring in the outward direction. So a pulling force, a tensile force on the spring. If, on the other hand, the spring is compressed, there must be a negative force on it, or a compressive force, so to give it a negative length change. So we can say that F equals K delta L if we're talking about the force on the spring rather than force of the spring. And this is going to be true. It's going to stay linear until at least the material reaches its what's called elastic limit. So if you start to deform it too much, then it's going to start, this is no longer true. You can see one example of this for a spring. If you were to try to compress it, at some point the coils start touching each other and then the relationship changes. So it gets a lot stiffer at that point. The spring constant for a beam with length L and uniform cross-sectional area A is K equals AE over L. We'll just take this as given for now. And E is a material parameter called the Young's modulus, also known as elastic modulus or elasticity. It's measured in pascals, force per area. K is called the stiffness of the beam, so the spring constant. When you're talking about a beam, often we'll call that the stiffness. Substituting this and rearranging, we can write the force in terms of the length change from our K equation up there. Force per area and delta L over L, relative length change, are also known as the stress and strain of the material. And now we've got a relationship that that doesn't depend on the geometry. It's the stress is equal to the Young's modulus times the strain. Young's modulus, again, just a material parameter. So we've got a relationship which is going to be true for all beams made of the same material. You learned in first year materials engineering that the elastic region only goes so long, and after that there's a different region. For a metal, typically we have an elastic region, then a plastic region, followed by fracture. It can also do all kinds of complicated things, like maybe necking, or maybe it's a brittle material where it would just have an elastic region and then immediately fracture. We're not going to be concerned with all of these failure mechanisms, just to remind you what's going on inside the material and why we would want to know what these stresses and strains are in the first place. This course is more about how the material moves and figuring out what the forces are, as long as we're staying inside the elastic region. Let's try to understand where this equation comes from. So this equation here that we substituted in, I just expressed that the spring constant was AE over L without proof. Let's see if this makes sense. So we've got that the force per unit area is related to the relative length change of the material. So the stress is equal to some constant times the strain. The constant is called the elastic modulus or elasticity. If the material is so-called highly elastic, has a big elastic modulus, that doesn't mean that it's really flexible. Actually, what it means is it's really restory. It's going to try and restore its position relative to after any perturbation, that is. So if you stretch the material out, it's going to try and restore it back. It's going to spring back to where it was with a strong elastic modulus. And if it has a weak elastic modulus, it's not going to restore back quite as well. So the stress that the material manifests is equal to E times the strain. Now, how does this stuff relate in terms of a material? Why would a spring constant increase as the area increases? Well, if the area increases, then we've got more material pulling. So looking at this on the other side, we get a bigger, it's really the stress, the force per unit area, that's equal to the elastic modulus times the relative length change. So because if the area is bigger, then the force goes up because we've got that same force per unit area distributed over more area. What about the relative length change in terms of length change and L here? So K, the spring constant, we knew from first year that goes down if you make the spring longer, other things equal. Why is that? Well, if you make the spring longer, then a given length change is less of a relative length change, right? So if the strain, imagine a strain is 1%, that means that the length change is 1% of the total length. If the total length is 1 meter, then that means we've got a 1 centimeter length change for a strain of 0.01. But if the total length is only 1 millimeter, then we've only got 10 microns to give the same strain. So the longer the spring, the lower the spring constant is. Okay, first of 3 examples. Compound cylinder with loading. So we've got this cylinder here and this cylinder here. They're both the same aluminum alloy, solid cylinders, and they're welded together at C. We're going to determine the axial stress in region AB, BC, and CD, subject to the loading shown. So there's no gravity. We're not concerned with anything in the y direction here. We've got a solid cylinder and another solid cylinder, and we've got this force applied at B in the right direction, 90 kilonewtons, 2 forces applied at C in the left direction, 65 kilonewtons each, 130 total, and this force at D, 40 kilonewtons to the right. What we're going to figure out is the axial stress in each of the 3 regions, and then the total deformation of the composite rod and the deflection of point C. So total deformation would be how far D moves to the right, because we got a fixed support here, that's not moving. So how far this moves to the right, and how far C moves, and where it moves. Maybe D moves actually to the left. So let's look at, qualitatively what's happening is we're pulling here, pulling back there, and pulling there. So there's a lot of different forces going on. So maybe B to C is going to compress because we've got forces on each end of it in the opposite direction. But C to D is going to extend. Okay, first step is to solve for the reaction at A. We can calculate what the areas are on each part of the bar before we do that if we want to set up our constants. And this problem is one-dimensional, again, because the bars are free and unloaded, and there's nothing going on in Y and Z, so we don't have to use the stuff from the next section, next lecture, that is. So at any point, we can just say that sigma is equal to E times epsilon, and E is a constant 70 gigapascals. So because the loading is changing, we've got a different load here than we do here, than we do here. So the stress is changing. We need to be careful about what axial force, what the axial force is as a function of distance. First, let's solve for the support. So in the x direction, we need whatever RA is to be equal to negative the forces in the right direction. So if we just want to solve for RA outright, instead of saying that it's equal to this net is equal to 0, then we find RA must be negative 90 plus 130 minus 40, but that adds up to 0, so there is no reaction at support A. We fixed everything else to be exactly to balance this out. So this is just a support in name only. It's only holding the thing from accelerating, but it doesn't even need to do that. It's just, it's doing nothing. It's there to make us feel better. So sigma AB is equal to 0, and therefore this is also equal to the epsilon. So the stress in this first area is 0, and so is the strain. From B to C, we have a compressive axial force of 90. So you can, if you were to continue your moving plane here, you can see on this side we've got 90 in this direction. So there must be a compressive force of 90 there. That tells us the stress by dividing by the area. And from C to D, we could look on the left side of it and say, well, we've got positive 90 and then we've got minus 130, or you could switch gears to looking on the right side of it and say that the force has to be equal to positive 40. The strain in each section again, is just sigma over E. And since the strain is changing with position, because for two reasons, actually just one reason, the stress is changing with position. You could say the two reasons are that the axial force is changing, and the other reason is that the area is changing. So instead of saying E is equal, or epsilon is equal to delta L over L, we have to be careful about this because every piece of it is going to have a different length change. So we got some length change for this, well, actually no length change for AB. We've got a length change for BC, and we've got some other length change for CD. We need to add up those length changes to figure out the net length change, or the net length change of the whole bar, the net position change of D and C. If you want to do this in a more general way, then you can redefine the strain as the rate of change of the X deformation with respect to X. So U is the total length change. I guess we should say, not length change doesn't make sense. This is really the total position change, or maybe the total X displacement. Yeah, total X position change of the piece at X. So U at X is equal to the integral of the X strain with respect to X from 0 to X. So this is, again, overkill. All you need to really do is find delta L over L for both the sections and add them up. But this is going to be much closer to how we're going to do things with FlexPDE once things get too complicated to handle with these problems we could do by hand. Substituting in the equations we found, so substituting in the force relationship, the area relationship, definition of stress, the Young's modulus we're given, definition of strain, and evaluating our change in length in terms of integrals, either from 0 to 9 or 0 to 0.5, where C is. Then we can figure out what the stress is as a function of position, and what the strain is as a function of position. Since Young's modulus is uniform, you just divide this by 70 gigapascals to get this, and come up with our length, our position change at D, which is the length change of the bar, and our position change at C, which is the length change of the partial rod AC. So what we found is that the entire bar moves to the right by about 53 microns. Not moves, the position D moves to the right by 53 microns, and the bar extends by 53 microns, and point C moves to the left by about 91 microns, meaning that its portion of the bar has compressed by 91. So this compressed by 91, this point moved by about 50, which means that this section must have extended by 50 plus 90, or 140 microns. Okay, let's look at another problem. This one's a bit harder than the last one. It's a complicated statics problem that involves length changes. This is about the pinnacle of, or one of the pinnacles anyway, of what Engineer 2 P04 gets to, and so it's also another milestone for us to be able to do these problems. So in the figure shown, this rigid bar, this bar here is rigid, meaning that it doesn't have a length change. It's got a Young's modulus which is very large compared to other things going on in the problem. ABC, this bar, the rigid bar, is pin supported at B and is connected to these steel rods, which are not rigid, AD and CE. The rods are 8 millimeter diameter and are threaded at their upper end with a pitch of 2 millimeters. 2 millimeters means the spacing between the threads is 2 millimeters. After being snugly fitted, the nut at A only, not at C. So we put this on, we close the nuts to the point where it's horizontal and there's no stress in any of the rods. And then we tighten A 2 full turns. So we say, you know what, there's just not enough tension in this problem. There's not enough tension in the world, so let's tighten this nut 2 full turns, which moves it down by 4 millimeters. However, that's not where things stay, or even where they are as soon as we're done doing that. As soon as we start tightening this, then we extend this. We put this rod into tension, which pulls it down, and that pulls this rod up, and they're going to reach some kind of a force balance. So we're asked to figure out the resting force in each rod after all this has happened, and the deflection of point A after all this has happened of the rigid bar ABC. Now at this point, you're looking at this saying, well, wait a minute, this is easy. These rods are broken. Look at that. There's nothing connecting them. So there's this whole question is just easy. Nothing happens. Well, this is just the way we draw it. Actually, the rod is completely connected. So nice try, but you're going to have to consider the extension of these rods. Okay, so AC is a rigid member, so it doesn't bend. Instead, we have the torque about B equation, giving us a relationship between the forces on each side. So 200 times this force has to be equal to 150 times this force. We could solve for the reaction force at B, but we don't have to, so let's skip it. And FA is equal to 3/4 FC is what we get from that. Now the length changes are also related. Let's also, in line with our previous question where we were using U as the position change of a piece of a rod in X, we're going to use V as the position change of a piece of a rod in Y. So if this moves up, then this has to move down. Specifically, VA over 200 has to be equal to negative VC over 150 because they're on this connected rod by this pivot. Finally, we know that in total, the deformations of A and C are related to the length change of the rods minus the amount each nut moved. So the position change of A is equal to its length times the strain that we're left with in A minus the movement of the nut down. So you can see if VA is really not is sort of the movement of the end of the rod at A. So if this moves down by 4 millimeters, then there's no strain in A because A didn't get in tension. We just moved the rod down. That would be what would happen if this wasn't connected. However, because C is connected, we've got to couple this equation with the equation that says that for every bit C moves up, we've got a strain in C as well. So in total, we've got force relationship because they're on this rod together. We've got the position relationship. As one goes up, the other one must move down. And we've got the position changes related to the strains in the rods. Then what we're going to do is the typical stress-strain relationship, that force is equal to area times stress. Area, we know, it gave us the diameter of the rods, and we know that stress is Young's modulus times the strain. So we get an equation like this for each of the rods. We've got an equation like this relating the length change to the strains and what else is going on in the problem, so that nut moving. And we've got a relationship between the one length change and the other length change, and we've got a relationship between the forces from our torque balance equation at B. That's 1, 2, 3, 4, 5, 6. In the unknowns, strain at A and C, force at A and C, and position change at A and C, so we can solve all that. And just to discuss the results, what we found is that VA is negative and VC is positive. So we found both the forces, yes, and then we found they're both positive, yet VA is negative and VC is positive. How's that possible? How did we find that both the forces are positive, yet the directions of motion are opposite? Well, it's because of that initial nut tightening that we did. So because we moved this, the equilibrium position down, VA has to be negative because of what was going on there. So we moved this down, and then it doesn't actually move down as much as we tightened the nut, though. It extends this a bit, because if it were going to move down, it would have to move this up by an amount, and C resists that. But not quite as well as AD resists motion because it's shorter and therefore stiffer. But let's look at what would have happened if we were to tighten both nuts. So what do you think? Just think about it for a little bit. We've got some competing effects here. So we've got, if we were to tighten both nuts by the same, then let's see, we've got this rod is shorter, so it's stiffer. This rod is also on the longer end of this, meaning that a given force here would would be more effective in causing it to rotate. And finally, a displacement here, a given force. So as this moves, we've got to have more motion here than we have here because of where they are. So more motion means more force. More force is more effective at creating motion. So it's kind of a set of different effects that that balance out to tell us which nut moves more. You can try messing around with it a little bit. As it turns out, we've got a situation where A still moves down and C moves up, although not quite as much as before if we were to tighten both nuts. One more problem for today, hung rod. The rigid rod ABC is hung by 3 identical wires. Knowing that X is equal to 2/3 of L up here, find the tension in each wire due to the force P. So the hint is assume that each wire extension is small compared to L. All right, so the trick is to draw this triangle at the start and say, well, let's let C go down by delta C, B go down by delta B, and A go down by delta A. Since P is a little bit to the left, you can imagine that it would slope this way, but if you end up getting it backwards, don't worry, it's all going to work out in the math anyway. Then look at this. So this is, if we draw a line horizontal from where C is, then you see that we've got a triangle here, and we've got another triangle making up the entire structure. And so we could say that because these triangles have the same angle, the angle is small, right? So we're not considering any kind of length change. Then we can write that this length, which is del B minus del C over L, must equal this length, del A minus del C, over 2L. So each wire, in addition to that, puts a force on the rod given by its length change and the spring constant. And we've also got, by substituting this relationship into there, a way to write all of this in terms of just the forces. Since in this question they asked us for the forces, the tension in each wire, we don't need to go about solving for the length change directly, although if we wanted it at the end, we could just substitute back in, assuming they gave us the spring constant as well. Okay, then we have that the net force on this rod is 0, so we'll write tension, tension, tension minus P equals 0. And the net moment about any point, let's say A, is 0, which means that X times P is equal to BL plus C times 2L. Okay. Remembering also that they told us X was 2/3 L. Solving all of those, we can come up with what the tangents are. And that's it.